Hey Aviva, I thought before I would start, I would show you my little drink corner because you always have tea in classes, so I thought I'd share mine. So these are all of my beautiful cups and glasses that I love, and this is my little tea and chocolate and coffee collection here. My favorite is chai tea or black teas, but I keep a little chamomile in there for my visitors because I absolutely hate chamomile and I will not drink it myself. Anyway, there's a little bit about my drink collection. Okay, let's get into charges. Okay, welcome to our properties of charge lab. So before we get into all of our demonstrations and explanations, I want to go over some of the basics of electric charge that we're going to need to know going into this. So for one, objects have electric charges based on the number of protons and electrons that they contain. So this has to do with their atomic structure, where they can have a certain number of protons, electrons, or neutrons. And based on the combinations of those, they're going to have electric charges. So if they have more protons than electrons, they have a positive charge. If they have more electrons than protons, they have a negative charge. If they have an equal number of both, it causes a neutral charge, and so we just say it doesn't really carry a charge, something like that. So a couple of the materials you're going to see me use a lot in this lab are the fur and the PVC rod, and I will continuously and repeatedly be charging up this PVC rod. So I'll do that by rubbing these two together. And what's ultimately happening is the PVC rod is being charged because of a transfer of electrons. So when charging occurs, it's always a transfer of electrons, not protons, and that's because electrons exist within the shell around an atom, where protons exist within the nucleus of the atom. So we're not going to be doing any nuclear explosions here and releasing protons. We're just going to be transferring electrons through their outer covalent shell. Hopefully. So the type of electric charge that I'm doing right now is called triboelectric charging, and that ultimately is charging through friction. So by physically contacting one surface onto another surface, creating some amount of friction, this is going to transfer electrons from one to the other. You'll notice that I'm using two insulators as well here. So the fur and the PVC are insulating materials. And that just means that they don't actually transfer electrons very freely like a conductor would. Conductors can share their electrons freely. They don't have a rigid electron structure in their shell, and so they can transfer those much more easily. So we're charging these two insulators by rubbing them together, creating friction, and they ultimately leave this process with a separate charge, one of them being positive, the other being negative. So the one that takes the negative charge is the one that just has a higher affinity for electrons. It's the one that'll like kind of attract or hold on to the electrons more readily than the other, even though neither of them like super want them. So the PVC rod in this case is going to be the one that takes the negative charge, and the fur actually is going to end up with a positive charge, although we don't really use it too much in this lab except for their triboelectric charging process. So anyway, I will be referring to this rod as being negatively charged throughout this process, and then we're going to see how it interacts with other materials like sugar and salt and styrofoam and aluminum, things like that. So let's get into it. Let's take a look at how this negatively charged PVC pipe interacts with salt and sugar. So the first thing I'm doing is electrically charging the PVC pipe by transferring electrons to the PVC. And then we're going to see how this interacts with sugar and salt. Now it's important to note ahead of time that sugar and salt have neutral charges. They don't carry an electric charge per se. And so what we're going to see is an interaction between them as I introduce the negatively charged PVC. Okay, first we'll take a look at sugar. And what I'm looking at is a lot of sugar particles that have been attracted to this PVC pipe. You can kind of see them bouncing around on there. Next, we're going to take a look at how this PVC pipe interacts with the salt. There's a really, really dramatic jumping and bouncing around of salt granules with an overall sticking of particles to the PVC pipe. So that's what's happening there. So why did the granules just happen to like magically attract to the PVC pipe? Especially because I don't know if it was easy to see, but I was not actually touching the PVC to either the salt or the sugar, and the granules still attracted. So let's talk about why that happened. One of the ways that charges interact is through induction, which is a process that does not require any contact, but it'll transfer charges or transfer electrons through different bodies. So let's talk about why that happened with the PVC and the sugar and the salt. Like I said before, sugar and salt are neutrally charged, and that's because they have the same number of protons and electrons in their atomic structure. They are not actually drawn like this because it's physics, not chemistry. So anyway, but you're gonna have equal numbers of protons and neutrons protons and electrons causing their charge to be neutral. However, they still do contain protons and electrons. So when you introduce a negative charge, like on the PVC pipe, what happens is a process called polarization, where as I bring my negatively charged PVC towards the molecules, the electrons and protons will separate to opposite surfaces. And the reason is because the negative charge in the PVC rod is attracting the positive protons and repelling those negative electrons. And so it causes the protons and electrons to polarize on opposite surfaces like this. Now, because this surface, this side of it is positively charged and my PVC is negatively charged, they attract. And so that's why we saw the granules jumping right onto the PVC pipe and having this attractive force. It was through an induction process, or charge by induction. So that's kind of what we were seeing there with the electrons and transfers of charge there. All right, the next thing we're going to observe, again with our PVC pipe and our burner, is an interaction between the system with the PVC pipe, which will be charged negatively, and this can, which I'm being helped by yerba mate. In fact, I had to open this can of yerba mate in order to do this, so I'm enjoying that. Anyway, so let's take a look at what happens between these two bodies when they interact. So I'm just transferring electrons again to the PVC pipe in order to create an overall electric charge. And let's take a look at what happens here. Okay. So notice that I'm working hard to keep the PVC from actually touching the can. It is not, in fact, touching the can at all, but it's moving. So let's talk about what we just saw with the can and the PVC rod. So you'll recall that when we did the salt and the sugar demonstration, that I said neither salt nor sugar carries a charge. They're both neutral. And so they were attracted to the PVC rod through that process called induction, where the positive charges were protons were polarized to one surface, and that surface ended up attracting to this negatively charged rod. I did a little bit of research on aluminum to see if it carries a charge, and actually aluminum does have 3 more protons than electrons, ultimately giving it a positive charge. So already the negative charge in the PVC is going to attract this positively charged aluminum just because opposites attract. So if this one's positive and this is negative, there's going to be a natural attraction between the two. In addition, I did not allow the rod to touch the can, and it was still attracting and rolling towards it. So part of that had to do with the fact that it already has a positive charge, but the other part of this has to do with the charging by induction, which again causes the protons within a surface to move towards that surface. Protons within a substance to move towards that surface closest to the electric charge, and then the electrons will move kind of to the other surface, and because of that, it just like kind of extra charges positively and creates this attractive force, which causes the rolling effect. So our next demonstration is going to be done with the electroscope, which I have designed here. We've already talked about two types of charging, triboelectric, which is the friction, and then also induction, which is kind of that transfer without touching. So I'm going to try and talk a little bit faster and not go into such details all the time, just to not make this take forever. So let's take a look at our next demonstration. Okay, so I'm going to charge up this rod, which remember is going to give us a negative charge. And then as I hold it next to this ball at the top, we're going to see that the little leaflets at the bottom inside the jar move slightly apart from each other. So the reason is because this negative charge, as I get the rod close, by induction, it causes electrons to enter the system. And because this metal is a conductive material, it readily receives electrons. As the electrons move throughout the system and down towards the little leaflets, both leaflets become negatively charged. And we know that like charges repel. So when the left and right leaf are both negatively charged, they're going to repel from each other. And as they move the rod away, they're going to come back closer together because they're not carrying that negative charge as much. Next, what we're going to do is see what happens to the system when I ground the system after charging it negatively. So let's take a look. So as before, I'm going to charge the rod. I'm going to transfer electrons to the rod, giving it a negative charge. Now I'm going to hold it next to the ball, which transfers by induction electrons into the system. We know because we see the leaflets moving apart. Now, as I'm holding it here, I'm going to ground the system by touching it with a finger. You see that the little leaflets kind of move together. I'll remove my finger and then remove the rod. The leaflets slightly move apart. Let's take a look at that one more time and see if we can really see it happening. Negative charge. I'm transferring that negative charge to the system so the leaflets move apart. I ground the system together, remove the rod, and now they moved apart. That was kind of nice. You could really see it. Let's talk about why that happened. So we know by induction that when I held the rod to the metal ball at the top, that I transferred the electrons into the system. Now, the system has a overall negative charge because it's carrying many electrons. When I ground it with my finger, the electrons are transferred into my body or kind of through out of the system. And so it leaves the ball with a neutral charge. But this rod still has a negative charge, and it's still right next to this here. So I remove my finger. The system, the metal system right here, is in a neutral charge because it's gotten rid of all of its extra electrons. And then as I move the PVC rod away, it actually forces a more positive charge into the system. It leaves the system with more protons than neutrons because I brought it into a neutral space, including these electrons. And then as I removed those electrons, it left this metal with an overall positive charge, and that's why we saw the little leaflets move away again. When they were both positively charged, they now have a repelling force, and so they move away, not because they're negatively charged this time, but because they're positively charged this time. Now that we've learned so much about electroscopes and how their charges are going to work with the little leaves at the bottom, it seems like we should be able to make some generalizations if we come across an electroscope in the wild. So if we were to come across an electroscope where we see that the leaves are separated already, we know that that means they're carrying a charge. But it could be either a negative charge where both are negative and so they repel, or the charge is positive, so they both are positive and they repel. So let's devise some kind of a test to tell whether or not the two charges here are positive or negative. Let's take a look. So one of the ways we could test if an electroscope has a positive charge on it, assuming that we don't already know it's positively charged, so we're testing to see if it is, one way we could do that is by introducing a negative charge, so carrying more electrons. If we introduce a negative charge to the electroscope, what we can expect to happen is that the protons in the system are going to be attracted to the electrons in the system. And so the protons that are already here are going to be attracting the electrons as well. And so there's going to be a transfer of the electrons into the system. Remember that electrons are the ones that can jump systems. Protons are contained in the nucleus of the atom, so they don't move from one atom to another, only the electrons. So if electrons are now entering this system, it causes the overall charge to become more neutral. And so these positive charges that were down here are going to be more neutralized by the entrance of electrons. And if these are neutralized, then the leaflets are going to move closer together. So that's what we would expect to see. The other option is we could introduce a positively charged rod as well. So if we introduce a positively charged rod, then the electrons that are in the system are going to want to leave the system. They're attracted to that positive charge. And again, electrons are the charges that move. So electrons will actually be exiting the system, joining the rod over here, and that leaves us with an even more positive charge in the leaflets, and they'll repel even further. So they're actually going to move further apart from each other. We can test for a negative charge in a similar manner. If we introduce a rod that has a negative charge, like the PVC rod, then the protons that are already present are going to be attracting those electrons. So electrons will be entering the system because they're attracted to the protons already there. And as electrons are entering the system, this becomes an even more negatively charged system, and so we're going to see that these repel. If we introduce a positively charged rod, like the glass rod with silk, charged with silk, so if it has a positive charge already, then the electrons that are present in the system are going to want to join the protons. So electrons are actually going to be leaving the system, causing a more neutral charge to be left over. So if electrons are leaving, then they're going to actually leave more of a balance with the protons in here. And so we'll see the leaves move inward into more of a neutral position. Okay, let's test our theory and see how it works on a real live electroscope. Okay, let's test our theory. So our electroscope has slightly separated leaves, and we're going to see if this charge is positive or negative. So what I'm going to attempt first is to introduce a positively charged rod. So I'm going to charge this up with silk. The silk is actually taking the electrons, in case you'd like to know. It has a higher electron affinity, so the rod itself will be positive. Let's see what happens. So we see that the leaves are moving further apart. So if this thing's positive, the rod is positive, it's going to attract electrons out of the system. And if the electrons leave the system, it means the system will be more positive. So if it's separating further, it must mean it was positive to begin with. Okay, let's see what happens when we introduce a negatively charged rod. Theoretically, it should take away the positive charge that we suspect is already there, and it'll put it into a neutral position. Which is what's happening. Ever so slightly, I believe. Yeah. As I move the rod in, you can see the leaves are moving towards each other. That's because the positive charge is moving. The protons are being attracted to the electrons on the rod, meaning that the leaflets are becoming a neutral charge, and so they move closer together. Okay, that was kind of hard to see, but it did confirm our idea with positive charge, which was that when we introduced a positive rod, electrons would leave, leaving us more protons, and they moved farther apart. That's what we saw first. The other option was to introduce a negative rod, causing protons to leave. And if the protons leave, that means there's fewer of them, this is less charged, and so they just move towards each other. That is what we saw. Okay, so the last thing we're going to do with the electroscope is discharge it. So I have a charge currently On the electroscope, you can see that the little leaves are kind of separated. I'm actually going to introduce this charged rod, show that they go back together into a neutral space. So they are carrying a charge on them like this. Okay, so now I'm going to touch my stove, which is metal and grounded, so this will be my ground. And then I will touch the electroscope simultaneously so you can see. Okay, so let's talk about what happens when you discharge an electroscope by touching a ground, like we just saw. So we know that electroscopes can carry either a positive or a negative charge. So when these two little leaflets are separated from each other, again, they're carrying a like charge, causing them to separate and repel from each other. And this like charge could either be positive because there's more protons in the system, or negative because there's more electrons in the system. So if it is carrying a negative charge, then by grounding it and discharging it like we saw, we're allowing those excess electrons to leave the system. If it's carrying a positive charge, and so it actually has more protons, then it actually needs electrons to enter the system in order to balance out with the protons and then neutralize the charge on the electroscope. So by grounding, that actually allows electrons to enter the system. Like Aviva said in a lecture once, the ground can be seen as like a sea of electrons. So we can either receive electrons from the ground or dispel electrons to the ground just based on what the charge on the electroscope already is. So that's what it looks like to discharge.